we will look at what we call the rank and basis of a matrix. But before that, let's look at one more example. So yesterday we were using Gauss elimination to solve a system of linear equations. Okay, so sometimes what will happen is you will have fewer equations than variables, or you may have more equations than variables. And then in each of those situations, we will look at what it is we need to do. So let's see this one here, where we have 2 x1 plus 4 x2 plus 2x3 is equal to 4. Then we have 3x1 plus x2 minus 2x3. This is equal to 1. We have 4x1 minus 3x2 minus x3. This is equal to 3. 4x1 plus 8x2 plus 4x3 is equal to 8. So this is our system of linear equations that we want to solve using Gauss elimination. So you notice here I have 4 equations, but there is only 3 variables. And if your system is consistent, what you will notice is that one of the equations is just a scalar multiple of the other, so it's unnecessary. But we do it the way we've always been doing it. We write down our augmented matrix. This is what our augmented matrix will look like with our coefficients here, 2, 4, 2. Then put a 4 here. 3, 1 minus 2, 1. Then 4 minus 3 minus 1, 3, 4, 8, 4, and then we have an 8 over here. So the goal is still to get a 1, 0, 0, 0, 1, 0, 0, 0, 1 here, and then we'll see what happens in the last row. Okay, so we can start by making this a 1. That's simple enough. We can divide the entire row by 2. So remember, in the test, you need to state what it is you are doing so I can see and follow your method, because there isn't just one specific way to do it. You can do it in several ways, mixing up the operations, but in the end, if you've done it correctly, we will both have the same answer. Okay, and we want to make this one here. Let's make this one here a 1, or a 0 rather. So we see that if I multiply this first row by 2, then subtract it from that one, I will have 0 here, and the same thing over there. And this row here, okay, let me just work on these 2 first, or maybe let's just do it. So here we said I need to say row 3 minus 2 times row 1, and the same thing, row 4 minus 2 times row 1. And then here I could multiply row 1 by 3 over 2 and then subtract it from this one. So we say row 2 minus 3 over 2 row 1. Okay, then I work this out. Let me just copy this to the next page. Okay, so our first row, we divide everything by 2. I get 1, 2, 1, and then this is 2. Then the second row, we say multiply this number by 3 over 2 and then subtract, so it will be 3 times 3 minus 3, that will give me 0. Then 1 minus 4 divided by 2 is 2, and then times 3 is 6, so it's 1 minus 6, which is minus 5. Then here I have negative 2 minus 3, which is minus 5. And then 1 minus 6, which is also minus 5. That's right. Let's see. This is 1 minus 3 over 2 times 4. Okay, yeah, that's 1 minus 6. So this is minus 5. Oh, I think even this one was minus 5. So the other one was minus 2 minus 3 over 2 times 2. Okay, minus 5. This is minus 5. Okay, and then the other one is also minus 5. So the entire row is just minus 5. Okay, so that you can do on your calculator. Just be sure you don't make any mistakes. Then the next row, we say multiply this by 2, and then subtract. So it's 4 minus 4. That will give us 0. Minus 3 minus 8. That will give us minus 11. Minus 1 minus 4 is minus 5. And then 3 minus 8 is minus 5. Okay, then the last row here, we said row 4 minus 2 times that, so it's 4 minus 4, that gives us 0. 8 minus 8, this will give us 0. 4 minus 4 gives us 0, and then 8 minus 8 will give us 0. So you can see we had an extra equation, and here, because the system is consistent, then the last row or one of the rows is just 0, 0. Everything is 0 in that row. So we continue with the top part here and make the identity there. So this one here, we can just divide everything by negative 5. Yeah, 1, 2, 1, 2 there. 0, 1, 1, 1. And even this one here, we can divide it by negative 1. So divide this by negative 1. So this is 0, 11, 5, 5, 0, 0, 0, and 0. So now we want to make a 0 over here. So I could just multiply this row by 11 and then subtract it from this one. So we say row 3 minus 11 times row 2, sorry. Okay, so I have 1, 2, 1. There's a 2 there. Then 0, 1, 1, 1. And then we say 11 minus 11 there, we'll get 0. Then 5 minus 11, this is minus 6. And then 5 minus 11 again is minus 6. The last row is just zeros. Okay, so this one here we will divide by -6. And then we end up with this matrix here. 1, 2, 1. 0, 1, 1, 1. 0, 0, 1, and 1. And then 0, 0, 0, 0. Okay, so we want to make zeros here and there. So we just say row 1 minus row 3. Here, row 2 minus row 3. So we have 1, 2, 0. Then 2 minus 1 is 1. Then 0, 1, 0. 1 minus 1 is 0. And then we have 0, 0, 1, 1, and 0, 0, 0, 0. Okay, so we need to make this one here 0, so we can multiply this row here by 2 and then subtract it. So this one here, we get row 1 minus 2 times row 2. So this is 1, 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, and 0, 0, 0, 0. And then from here we can tell what our x1, x2, and x3 are. So here, this means x1, because we have x1 plus 0 is equal to 1. So this means x1 is equal to 1, x2 is equal to 0, and then x3 is equal to 1. So we've solved this one. So this was an equation that had, this was a system rather, that had more equations than unknowns. And because it is consistent, you will see that one of the rows is just becomes 0, 0, 0 because it's a scalar multiple of the other. Okay. So we look at what is called a unit column matrix. So a unit column matrix. This is a matrix that has a 1 and zeros everywhere. So this matrix has a 1 and zeros everywhere else. So it's a column matrix. So it is one column, however many rows it has. There is only one row, there's only one number 1 in the column, and all the other entries in the column are zeros. So if we look at our matrix over here, this one here, this is a unit column matrix because there's a 1 here and all the other numbers in the column are zeros. This one here is also a unit column matrix because there's only one 1 and all the other numbers are zeros. This one here is also a unit column matrix because there's just one 1 and all the other numbers are zeros. So we only look at the coefficients, not the solutions. Okay, so when we're looking for the rank and the basis of a matrix, what we want to do is figure out how many of these unit column matrices do we have. Okay, so you want a unit column matrix where there's only one 1 in that column and all the other elements are 0. And then you count how many of those do I have. So over here I have 1, 2, 3. So this one will have a rank of 3. Now the way we count them is the position that the ones are at matters. So if I have something like this, if I have 1, 0, 0, 1, 0, 0, 1, 0, 0, and here I can have my A, B, C like this. Even though each of these is a unit column matrix by definition, when I'm looking for the rank, I'm not just looking for how many of these do I have, I'm looking for how many unique ones do I have. Because if I look at the first one, the 1 is at the very top. So it's a 1, 0, 0. And if I look at this one, the 1 is also at the very top. So there's no difference between this unit column matrix and this one here. And the same thing with this one over here. So here, what we are doing when we're looking for the rank of a matrix, we are looking for unique column matrices. So we say that our rank of a matrix, this is the maximum, it's maximum number of unique unit column matrices that can be obtained. Okay, so you start with your system, you perform Gaussian elimination as far as you can, and then you count the columns that have a 1 in a unique position. So if I have a matrix like this, let's say this is 1, 0, 0, 0, 0, 1, and then 1, 0, 0, like this. If that is, let me just write the augmented matrix. And then here I have 0, 1, 3. So this one here is matrix of rank 2 because there are only 2 distinct column matrices. So the first one is this one here, and the second one is that one here because the position of their ones are different, so I count them as individuals. I'm not going to count this one as the third one because the position of the 1 is the same as the position of the 1 in this one. Okay, so this matrix here will have a rank of 2, while this one here has a rank of 1. Okay, now with these matrices, like I said before, the way you perform your operations, you can follow any procedure. Like here, if you look at what I've been doing, I've been saying row 2 minus this one and then this. It's the path I've been following, but you could do it another way. And even though the position of your ones is not the same, if you have done it correctly, we will always end up with the same number of of unit column matrices. So if a matrix has a rank of 1 like this one, even if we take different paths to get to this point here, you will notice that the rank of the matrix is always equal to 1, no matter how you perform the Gaussian elimination, because like I said, it's not a unique path. There isn't just one way to do it. There's several ways that you can work it out. Okay, then from the rank of the matrix, we have what is called the basis of the matrix. And the basis of the matrix are just those variables. It's a set of those variables that give you the column, the unit column matrix. Okay, so here, when you have a rank of 1, your basis, you can see that x1 here gives you a unit column matrix. X2 gives you a unit column matrix, and X3 also gives you a unit column matrix. But we say that the rank is 1, so that means our basis must only contain one of these variables. And here, because each of them equally gives us a basis, we can pick any of them. So the basis is not always just one specific answer, especially when you have maybe 3 variables and your rank is less than 3. Then you can pick your basis. So here I can say my basis is equal to x1 if I decide to pick the first one. So my basis, the number of variables I put in the basis must be equal to the rank. Okay, so I have my basis and I've decided to use the first variable. Somebody else could say the basis is equal to a set containing x2. They are equally correct. Okay, so matrix doesn't necessarily have just one basis, but what you notice about the basis is they contain the same number of elements. So if the basis that I've picked has only one variable, if you pick a different variable, then your basis must also have only one of the variables. So somebody else could pick x2 as their basis, and another person could pick x3 as their basis, and so on. Okay, but you can see from here the maximum value of the rank is 3. Your rank cannot be more than 3 because you cannot get more than 3 unit column matrices when you have a matrix like this. Okay, so rank is just the maximum number of unique column matrices. We said unique, looking at the position of the ones. So here, when we look at this one, this is unique, this is unique, this one is not unique because it looks exactly like that one. Okay, so here my rank will be 2, and then I can say that my basis over here is x1 and x2, or I could say x2 and x3. Notice x2 is always included here, okay, because these two, x1 and x3, are the same. Their unit column matrices are the same, so it's x2 and one of the others. Okay, So here I was free to pick any of them because all of their unit matrices are the same, but over here only x1 and x2 look the same, so I could pick between them, but x2 was unique on its own. It doesn't resemble any of them, so it's definitely in the bases. Then we have what is called the basic variables. So the variables that you put inside the bases, those ones we call them the basic variables. So here x1 is basic variable. So here x1 and x2 for this case, because those are the ones I've picked, those will be my basic variables. And then the variable that I don't pick to be part of the basis, or the one that is not part of the basis, that is what we call a non-basic variables, or non-basic variable. Okay, so here we can see that x3 is non-basic just because it is not part of the basis. X2 is also non-basic because it is not part of the basis. Here in this case, X3 is non-basic. Why? Because it is not part of the basis. Okay. Right, so remember what we were, or what we are doing over here. We're trying to solve a system of linear equations. So we want to find out, we want to get a value for x1, x2, and x3. So when we have the rank and we have the basic variables, we still want to give some type of answer and say x1 is equal to this, x2 is x2 is equal to this, and x3 is equal to this. So the way we do that is we take our non-basic variables and we equate them to letters. We say A, we can say x2 is equal to A, and then x3 is equal to B, where A and B are any real numbers. So let me call this one number 1, then this one will be number 2. So if we have something like this, we have our system over here. We've done the Gaussian elimination. Let me just pick numbers here. Let's say 2, let's say 0, 0, just so it looks good. Okay, so here we've done Gaussian elimination, and then this is what we have. We've determined our rank, and we've chosen our bases to be x1. Now we want to come up with something like x1 is equal to this, x2 is equal to this, and x3 is equal to that. So what we do is the non-basic variables. So for number 1, our non-basic variables, we say x2 and x3. We equate them to some numbers, some real numbers, any real numbers. It doesn't matter what they are. Okay, so we say the non-basic variable, the first one, which is x2, the first non-basic variable, we call it A. A is just representing any real number. And then the second one, B, x3, we'll call it B. And then what we want to do is write the basic variables in terms of our non-basic variables. So we look at this equation here. This is x1 plus x2 plus x3 is equal to 2. So we have x1 plus x2 plus x3 is equal to 2. So this means that x1 plus A plus B is equal to 2. and then we can say x1 is equal to 2 minus a minus b. And then our solution here, so our solution, I think the book right here, x1, x2, x3, this will be equal to 2 minus a minus b, and then this is a, and then this is b. So here our solution is not just a specific number like with the others that we have done so far, but our solution is in this form. So that means if I pick my x2 to be some number, let's say 5, and then this one to be 10, then if I write x2 as 2 minus 5 minus 10, that pair will be a solution for that system of equations. It'll work. Okay, let me see. Okay, right. So I can pick A and B to be any variables that I want, any real numbers that I want, like I said. So I can pick A to be 5 and this one to be 10, and then I can work out x2. So if I let A equal to 5 and b equal to 10, then this means that x1 is equal to 2 minus 5 minus 10, which is minus 13. So this is one of the solutions. x1 is equal to minus 13, x2 is equal to 5, and x3 is equal to 10. So this would be one of the solutions. And when I substitute it back into the original equation, into the original system, it will satisfy it. So you can see it is possible to pick any value for A and B. And just so that everybody has a unique solution, we let the non-basic variables equal to 0. So if A is equal to 0 and B is equal to 0, so we let A equal to 0 and B equal to 0, then our solution x1, x2, and x3 will be, the first one, x1, we said it's 2 minus 0 is 2, and then we have 0, 0 like that. So x1 is 2, x2 is 0, x3 is 0, and you can see when I substitute it back in here, it does satisfy it. So there's an infinite number of solutions that we have. Yeah, there's an infinite number of solutions that we have, and one specific value that we take is when the when the non-basic variables are equal to 0. So we can look at this one as well. Let me just change this to 0. Okay, so this is the matrix that we have after Gaussian elimination. We say that this matrix has a rank of 2. Okay, because there's only 2 unique unit column matrices. And then we say that our basis, or at least one of them, is x1 and x2. So our non-basic variable is x3. So that is the one that is not part of the bases. So now we want to rewrite x1 and x2 in terms of the non-basic variables. Okay, so we can let x3 equal to a, where a is just any real number that we have. Okay, so for this one here, we can see that x3 is equal to 3, because that one you can easily solve it. So we will say x1 plus x3 is equal to 0, but x3 is equal to a, so we have x1 plus a is equal to 0. So this means x1 is equal to minus a, and for this one, x3 is just equal to 3. So when we write down our solution of x1, x2, and x3 here, the solution for x1 will be minus a, we have 3, and then we have a over here. Okay, so that is our solution like that. And the usual one that we pick is when a is equal to 0. So here you'll have 0, 3, and 0. Okay, now let's look at an example where we have to use Gaussian elimination, and then from there we have to work out the rank, the bases, and then our solution. Just see if I can get an example. Okay, this is from the exercise 6.1, and look at question 2, where it says determine a basis. So you can see it says determine a basis. That means it's not necessarily just one answer. Then the rank of the augmented matrix, and then if it exists, a solution and the general solution. So the general solution is the one where we make the non-basic variables equal to 0. So let's look at 2 and number 1. No, I don't want that one. Let's look at 2, number 2. So say 2.2. So we have this one, x1 plus x2 plus x3 is equal to 4. 2x1 plus 5x2 minus 2x3 is equal to 4. So we want the rank, basis, and basic solution and general solution if it exists. Okay, so doing that, you form our augmented matrix as usual. So this is 1, 1, 1, 4 here. We have 2, 5, minus 2, and then 4. So there's already a 1 here. We can try and make this one here a 0. So we can multiply this by 2 and then subtract. So we say row 2 minus 2 times row 1. So this is 1, 1, 1, and 4. Then 2 minus 2 is 0. 5 minus 2 is 3. Minus 2 minus 2 is minus 4. And then 4 minus 8 is... Okay, did I copy this question right? Let me just check here in the book if I did this right. Okay, yeah, I see. So this should be a 3, not a 4. Okay, so then I say 3 minus 8. This gives me minus 5. Oh, sorry. This is a 3, so minus 5 goes over here. Okay, and then this row here, I can divide it by 3. Then I have 1, 1, 1, 4, 0, 1, minus 4 over 3, minus 5 over 3. Then we can try and make this one here a 0, or even that one there is 0. See, so to make this one here a 0, I just subtract. So I say row 1 minus row 2. Me 1 minus 1 is 0. 1 minus 4 over 3. That 1 minus negative 4 over 3. This is 7 over 3. And this is 4. Okay, not 4. It's 4 minus negative 5 over 3. 4 is 12 plus 5 is 17. And then this one is 0, 1 minus 4 over 3. And then this one here is minus 5 over 3. I'll just take it to the next page. Okay, so that is minus 5 over 3. So that is what I have. Okay, so you can try as much as possible. You cannot make these ones with a 0 and a 1 without changing one of these. So here we can stop and say that we have a rank of 2. So the rank of this matrix is 2. And even if, like, you think about it, even if I had a 1, 0 here, then it's the same as this one. Or I have a 1, 0 there, it's the same as that one. So it's not going to change the rank of this matrix. So the rank of this matrix is 2. And then the basis, or a basis, is this one here, x1 and x2. So this is x1, the column of x1, because it has 1 and zeros everywhere else. This one also, it has 1 and 0 everywhere else. And then this one is our non-basic variable. So our non-basic variable is this one, x3. Okay, and then from there, we let the non-basic variable equal to a. So we let x3 equal to a, and then we rewrite x1 and x2 in terms of a. So here we have x1 plus 7 over 3, x3 is equal to 17 over 3. So we say x1 plus 7 over 3, x3 is equal to 17 over 3. So this means that x1 plus 7 over 3a is equal to 17 over 3. So this means x1 is equal to 17 over 3 minus 7 over 3a. So here I've written a basic variable in terms of a non-basic variable. And then the second one, x2, I do the same thing. We have x2. This is equal x2 minus 4 over 3 times x3 is equal to minus 5 over 3. This means that x2 is equal to minus 5 over 3 plus 4 over 3 times a. Okay, then I can say that general solution we can write it in this way. x1 is 17 over 3 minus 7 over 3 times a. Then the second one is minus 5 over 3 plus 4 over 3a. And the last one is just a. So this is a row matrix, so there's no commas here. And this, I can write it, I just want them to be on the same page. We put a T here for transpose. This is equal to x1, x2, x3. Again, another row matrix. So here I can see x1 is equal to this one. There's a transpose there. x2 is equal to that one. x3 is equal to that one. So this is the general solution. And then our basic solution we let x3 equal to 0. Then we will have x1, x2, x3. This is equal to 17 over 3 and minus 5 over 3 and 0. Okay, so those are the 4 things that we're looking for, 4 or 5 things. The rank of the matrix, you just count the unit column matrices, the basis, the variables that gave you the unit column matrices, those are your bases. Non-basic variables is just the the variables that are not included in your bases. And then to find the general solution, you let the non-basic variables equal to a, where a is any real number that you want. So the general solution is in terms of a, and then the basic solution, you let a equal to 0. And number 3, very quickly, we have x1 plus x2 plus x3 is equal to 4. 2x1 plus 5x2 minus 2x3 is equal to 3. Then x1 plus 7, x2 minus 7, x3 is equal to 5. So again, we write the augmented matrix 1, 1, 1, and then 4 here. Then 2, 5 minus 2, then 3 here, 1, 7 minus 7, and 5. So again, we perform our Gaussian elimination, so we can make this 0 and that one 0 there. So this one, we say row 2 minus 2 times row 1. Then this one is row 3 minus row 1. So the first one does not change. Get a 4 there. Then 2 minus 2 is 0. 5 minus 2 is 3. Minus 2 minus 2 is minus 4. And then 3 minus 8 is minus 5. Then the last row, 1 minus 1 is 0. 7 minus 1 is 6. Minus 7 minus 1 is minus 8. Then 5 minus 4 is 1. Okay, then we can try and make this one here a 0. And to do that, we just say this row times 2 and then subtract it from that one. So we have row 3 minus 2 times row 2. So what we'll get is this 1, 1, 1, 0, 3, minus 4, minus 5, and 0. Then 6 minus 6 is 0. Minus 8 minus negative 8 is 0. And then 1 minus negative 10 is 11. Now, when we look at this matrix over here, we can see the last row is not made up entirely of zeros. I have 0, 0, 0, and 11. That means we have 0x1 plus 0x2 plus 0x3. This is equal to 11, and there's no way this is possible because this would mean that 0 is equal to 11. So this is what we call a contradiction. Okay, so it is not possible. With the other one, we got 0, 0, 0, 0, which makes sense, but there's no way you can add 3 zeros and then the answer is equal to 11. So whenever you get a situation like that where one of the rows, the variables are zeros, but the solution is not 0, we say that our basis is the empty set. We write it like this. So it is the empty set, or it does not have a basis. And the rank of this matrix is 0, and it has no solution. Okay, so if I got a 0 over here, that's different, because if I have 0x1, 0x2, 0x3 is equal to 0, that makes sense, because the left-hand side is 0, the right-hand side is 0. But here on the left-hand side, I have 0. On the right-hand side, I have 0. I have 11. That is not possible. Okay, so even though you can see that I could probably make this one a 0 and this one a 1 and then say the basis is 2. You don't do that because of the contradiction that we have there. So don't just continue and make this one a 0 and then you count your rank as 1, 2. That is not correct. What you should do here is notice that there is an inconsistency in the last row, which is a contradiction. That means your basis is the empty set, your rank is 0, and it has no solution. You don't need to proceed any further. Okay, tomorrow we will look at some more examples from that exercise where you have to determine the rank and the basis of the matrix. Remember, the test is on Friday. I think the time will also be 12:30, probably in the basement, so please be there on time. But as soon as I know for sure, then I will let you guys know.